Hey everybody, and welcome back. If it's your first time here, welcome to this channel. I'm David Townsend. This is the Net Academy, where we are learning networks together. And on this video, what I'm doing is I'm actually starting a brand new series, a brand new collection of videos that are covering two protocols, but they're referenced together. That is EVPN VXLAN. Yes, they are different protocols, but some people think they're actually the same. They're not. So EVPN stands for Ethernet Virtual Private Network. VXLAN stands for Virtual Extensible Local Area Network. That's two big acronyms in one there. But this is the first part. This is the first video in this series. And what we're going to do, as always, is start off with the basics. There's going to be no lab in this video. There's not going to be any configuration. This is actually just going through the initial concepts and understanding what is EVPN, what is VXLAN, why do they work together, what are the key terms for both of these protocols, and how do they actually bring benefit and value to service provider networks, to enterprise networks, to campus networks, and to data center networks. And so just by saying that, you can actually hear that these are deployed quite a lot throughout the world already. Maybe not in conjunction with each other all the time, because as I said, they are two different protocols at the end of the day. But really for the enterprise, for the campus, and for the data center networks, they are actually becoming more and more common because of all these benefits they actually bring. So again, on this video, we are going through the basics. We're covering the introduction, key terms, benefits, and how these two protocols work together for these different types of networks. So let's get going on the theory and build up from there. Okay, so here we go. And as you can see, there's a few switches, multi-layer switches specifically, or routers, whatever you want to think of them. They're all connected together and they've got different connections to and from each other. So if we look at it from this switch here, it's got connectivity up to this switch here, or that router, and all the way over to here as well. So utilizing this path here and this path here, if this link goes down, it's still got connectivity to this switch and to that switch as well. I'm just going to call them switches just for simplicity. So it's a very straightforward connection. Now, how does EVPN and VXLAN actually come into this? Well, first I want to look at it from a traditional legacy type of approach when it comes to networking. And of course, and I'm not calling these traditional, but because they're still in use today, but what we have are VLANs, or virtual local area networks. And let's just say, just a rough number, just any number out there, that this is VLAN 500. And within VLAN 500, you've got X amount of users with their own devices, laptops, tablets, or CCTV cameras, IoT devices, whatever it may be. You've got a user, a device within VLAN 500. And it will consume an IP address. So let's just say it consumes 192.168.10.10/24, just for example. Again, just a rough number. Now, say for example, all the way over here, you also have VLAN 500, where there is another user or a server or a application that user all the way over here actually wants to access, wants to use. And let's say it has the IP address of 192.168.10.11, again with a /24. Now, how can these devices, whatever they may be, actually communicate with each other? Well, what you could do is you could actually have layer 2 here, and 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 I think that's all of them, and layer 2 there, missed one. So what that would then allow is for this virtual local area network to feel like it's in the same geographical area, because what we're doing is we're trunking VLAN 500 all the way from this switch here, let's call it switch 1, up to switch 2, or maybe switch 3, and all the way down to switch 4 here. So it'd be quite literally be trunking up to here, or across here, and then down to this switch here via these two routes. However, what is the problem when you start having layer 2 everywhere? The problem is something called STP, or Spanning Tree Protocol. Now, this is a protocol which really limits networks. I'm not saying it's a bad protocol. It's actually very, very good in what it does at layer 2. But it does so by blocking ports, by not allowing ports to be actually passing traffic, and thus preventing a layer 2 loop. Because if, say for example, and if this was a spine only topology, what you'd have between these two spines is actually a connection itself. And if a layer 2 VLAN packet, or frame I should say, is trunked up to here, it could then be trunked over here as well, and then back down to this switch it goes, and it keeps going round and round and round like that, and you've got a layer 2 loop essentially. Additionally, what if you then add in another switch, and you just give this a few ports just for example, and you connect this switch here up to switch 1, I think I called this. But you maybe say, well, for redundancy, for resiliency, I also want this switch to be connected. And for redundancy or resiliency, you might say, well, I also want this switch to be connected over to this switch here. Let's just say that's switch 5. Now, that in itself sounds great, but with the spanning tree protocol, and there's different variations of this, you've got STP, you've got RSTP, you've got MSTP, and you've got proprietary Cisco implementations as well, like PVST, PVST+. They're just proprietary, there are standard implementations of them, of course. But the point is that whenever you add in an additional network device into this spanning tree protocol domain, it is going to start sending out and receiving bridge protocol data units, or BBTUs. And what they're basically doing is they are running that STP algorithm to calculate who is going to be the root bridge, i.e. the root switch of this STP RSTP domain, and what is the actual cost to get there. And they may do that for all VLANs or on a per VLAN basis. We're not going into STP, but to do this, what they would do is they would say, well, actually, I'm going to block this port here. So even though this switch here has got 2 uplinks into the campus fabric, or maybe to the data center, if this was a data center, only one of them is actually working because STP has automatically blocked this port, maybe, to prevent any type of loops from taking place. So STP, whilst it works great, it doesn't allow for full bandwidth, for full resiliency, because by its very nature, it's blocking ports. And let's carry on with that. How can you actually get around spanning tree protocol? Well, of course, one of the ways is to have layer 3 everywhere. So you'd have layer 3 here, and you would have layer 3 here, layer 3 here, layer 3 there, layer 3 here. Basically, all of this would be layer 3, and maybe you'd have a /31 address here and a /31 address here, or maybe even a /30 address here, or whatever. This is high level, this is just introductions. But remember what I said a few minutes ago, where over here we had VLAN 500, and over here we had VLAN 500 as well, and we had users in here, we had devices which were consuming IP addresses. Now, can that VLAN go over this fabric when it is a rooted fabric? The answer is no, because VLANs work at layer 2. Whereas here we've got I'm going to write it here, we've got IP, we've got Internet Protocol, we've got routing protocol, whatever the underlay is, OSPF, ISIS, whatever, it doesn't matter. Layer 2 VLANs cannot span over a layer 3 network. They quite literally stop here. Wherever that IRB, or integrated routed and bridged interface is, so it'd be something like IRB.500 just for example, that would be the gateway for this host to get out of that network, to get out of that switch, to get out of that router, to get basically out there. So VLANs do not go past that IRB interface. Everything from here up is routing. That actually presents a problem. The problem is, again, if I just draw my host, I keep deleting them for some reason, is that actually these hosts can move. So maybe the host here moves over to this switch over here. So now this switch here needs tag 500, but also this device here, this host, needs to learn that user A has moved over to switch 5. Now, how is that switch actually going to learn of that? Also, how is it going to get the information, those frames, from now this switch or even the original switch up to this switch and down, or from this switch where it roamed to and back down via whatever path. And that is where EVPN and VXLAN come into it. But let's look at VXLAN first. So let's say that that user, again, I'm drawing them, I keep deleting them, I do apologize, but it's good for my artistic skills. So let's say, again, these users here are in VLAN 500 here. And to actually go through how to resolve that problem, let's first look at what a VPN or virtual private network is. Just very high level here. So let's say, for example, we've again got our users here. So this would be me at home, and maybe I'm consuming an IP address of 192.168. Again, it's just do 10.10 just to keep things consistent. And then I've got access to my missed access points here. So I'm just going to draw in missed. So it's just an access point, which then goes into, at some point, the internet itself. So I'm just going to do internet here. And somewhere out there will be my corporate resources, will be all the tools I need to do my day-to-day job. So let's just draw here, and this is a terrible drawing, I know. Let's just draw a server here, and this is consuming just an IP address, just for example, 10.10.10.10, whatever, //16. Now, is my traffic that's coming from my laptop, from my tablet, whatever it may be, as it goes through the missed access point, through the internet, and eventually hits the server here, do I want that information to be sent over the internet in a insecure way? Of course not, because no one really governs the internet. So what there then is this concept of a VPN. Now what a VPN basically does, and it wouldn't be from the missed access point here, well, it actually could be, but just from the missed access point here, is what you'd establish is a VPN tunnel, which would then tunnel all my traffic through this virtual private network over the internet till it gets to the corporate network, and then it comes out from there and it hits the server, and the server responds back through that tunnel and back out the information it actually goes. Now, of course, you can add on internet key exchange and encryption algorithms, etc., to make that traffic actually secure. But all a VPN is it's a tunnel at the end of the day, and this is not too dissimilar to what we're actually doing with VXLANs. So again, drawing the users, and apologies, I know I keep doing it, but it's good practice for my artistic skills, he says. So here we got VLAN, a user in tag 500, another user here in VLAN 500. Because all of this here is layer 3 and everything down from here is really layer 2, what this device here would do is it would build a tunnel which goes, yes, of course, up to here or up to here, and then down from there it goes. But it would build a tunnel, so all of this user's traffic coming into the ingress interfaces and out the egress it goes, actually goes through the tunnel over the layer 3 network it goes, where it comes out the other end into the egress interface, out of the ingress, or in that case it would be the egress interface, but eventually it hits the user there. That is all VXLAN is actually doing, is it's a virtual extensible local area network. We're actually extending that layer 2 network using VLANs over a layer 3 network itself. But why do you actually need to do this? The reason why, and this is the VXLAN header actually shown here, but let's go through the VLAN header. So over here, I'm just going to do VLAN. I'm not going to draw it out, but what you have within a VLAN header is you have a tag protocol identifier. That is 2 bytes, which basically identifies what is the type of VLAN. Is it a customer VLAN, is it an SVLAN, or is it an EVLAN? You will then have 3 bits which go towards the priority field. Is it low priority, medium priority, or high priority? You'd then have 1 bit to a DEI, or drop eligible indicator, depending on the type of VLAN. The big part here is you then have 12 bits. I'm just going to draw a line of separation. You'd have 12 bits which actually go to the VLAN identifier itself. Now that sounds a lot, 12 bits, but a bit can be a 0 or a 1. So you've got two options there, 0 or 1. So if you do 12 bits to the power of 2, you then come out with 4096. So out of 4,000, I'm just drawing it again here, out of 4,096 possible identifiers, only around 4,094 are actually used, because vendors, we like to have a few in reserved, and maybe they have standard reserve uses. I don't know, but you're not getting the full value of 4,096. But in data center networks, this is absolutely not enough, because they've got so many applications running, they've got so many resources actually being consumed, so on and so forth. It is by far not enough, and that's becoming more common in campus fabrics as well. So where does the VXLAN header actually come into this? Well, if you look at the header here, what you've got is the VNI, or virtual network identifier, and that is 24 bits long. If you do 2 to the power of 24, what you'd actually come out with is around about 17 million. So VXLAN can support just under 17 million virtual network identifiers. So that is very, very powerful, especially for the data center, because it's allowing each tunnel to have up to 17 million different, it's only going to have one, but 17 million different options of an identifier to actually pick from, to be configured to use, to tunnel that traffic over. So the benefit of VXLANs is not only do they allow to tunnel traffic, layer 2 traffic over a layer 3 backbone, but it also allows a huge amount more of identifiers. An identifier, it's the same concept as a VLAN identifier. It's identifying that tunnel. It's identifying the traffic that will go through that tunnel between two switches or routers. And there's an actual term for those, and we'll come on to them in just a minute. And I'm almost missing a big point here. Note here, all of these additional headers that happens whenever we start talking about VXLAN. Now, there's a key term, and I don't want to go through it too much just yet, but I will say the word VTEP. I'm not going to go there just yet. We're going to cover these terms in a few minutes time. But what you would have is you'd have a VTEP here and you'd have a VTEP here. Essentially what a VTEP does is it builds that tunnel over that layer 3 network. So what the VTEP actually does when you've got that user that is sending that information is it will take that original Ethernet frame. So it takes that original IP address, source destination IP address, it will take that original source destination IP address, etc., and it will just encapsulate that within the VXLAN header. So what we actually have is the IP and the MAC, and that would be the original information that this host is actually sending. But then the VTEP, it does something called encapsulation, i.e. it's then going to encapsulate all of this information in and with new additional headers. So, and as you can see, it's going to add in a destination port. So I'm just going to do DP there for destination port. Now for VXLAN, that is specifically 4789. That is just the standard port number for VXLAN. You're also going to have a source port as well. And of course, you've then got a destination IP, source IP, and over here, I'm just going to do it in one big header. You've got your source and destination MAC addresses as well. So basically what the VTEP is doing is it's adding IP and UDP headers to that original Ethernet frame and with those IP packets. It's just encapsulating it all, adding on a shim header as well. So you'd also have the VXLAN header here. I forgot to include it, which was a bit silly because this is all about VXLAN. But you'd have what's referenced to as the shim header as well. If you're wondering what the shim header is, it's basically this just here. A lot of the VXLAN shim header is actually reserved. You've got reserved bits here, you've got reserved bits here. Only 24 bits actually go to identifying what is the virtual network itself. And then you've got some flags here as well. So not a lot of that VXLAN shim header is actually used. But the big point here is to go for this VTEP to go over this layer 3 rooted network. It encapsulates the original frame and it adds in the VXLAN shim header as well as IP UDP headers as well. Otherwise it wouldn't be routable. And once that information is added, we can then, or the VTEP can then send through that tunnel to the destination that layer 2 traffic. And when it gets there, it basically just strips off all of the headers that you see here. It will just get rid of the VXLAN header, get rid of the UDP header, get rid of the IP headers, get rid of the outer MAC headers, and then you are actually left with the original Ethernet frame, or that original Ethernet frame with IP header information and maybe with VLAN information as well. That's essentially what VXLAN is it's allowing you to tunnel over layer 3 network, layer 2 - layer 3 traffic, really layer 2. But here's the question. If we've got our host here in VLAN 500 and we've got another host here or another device or a server, whatever it is, that needs to be accessed again in VLAN 500. And as I said, we've got this VTEP here. How does it know, big question mark here, how does it know where this destination actually is? How does it know that it's over here? How does it know that it can get to this destination via this route or even via this route? That is where the world of EVPN actually comes into it. EVPN is an Ethernet virtual private network. It is a VPN, as I said before. It's a tunnel to net technology, but specifically for layer 2, specifically for Ethernet. So EVPN, although it can advertise layer 3 information, it's really working at layer 2. It's working at the MAC layer. EVPN in itself is a massive protocol, and that is because it comes from the world of BGP, or Border Gateway Protocol, specifically multi-protocol BGP. BGP is a beast of a protocol at the end of the day. EVPN is huge. MPBGP is even bigger, and that's because what you can do, just for example, is you could configure these devices up here as route reflectors. So any routes that come into the network are automatically reflected down from the route reflectors. And also you've got aspects such as path attributes, or PA, which actually can influence the way traffic is routed throughout the network. You've got confederations as well, and you've got these other key terms that we're going to go through, such as route targets, route distinguishers, and so much more. BGP at the end of the day is huge. But what you need to know, just from what I just said, that EVPN is really just BGP, but at layer 2. But coming back to my original point, how does this host here know how to get over to this server, this host, all the way over on this switch actually here? Well, that is where EVPN comes into it. When this host sends a frame into this switch, it's initially going to do what's called an ARP, a address resolution protocol. And the switch at that point, when it sees this host source MAC address, it's going to update its switching table saying, yeah, out of this egress interface, I've got host A with this MAC address. Now, that's great, but with traditional Ethernet, what you have is a flood and learn approach, where what would happen without EVPN is that for all layer 2, this switch would then flood out of all interfaces here that this MAC address has been seen. We don't actually want to do that. We only want to advertise to interested parties that this host is connected to this switch. So what EVPN does is when that MAC address is entered into the switching table, if there's another interested party, shall we say, in VLAN 500 within that VNI, that virtual network identifier, within this network, what EVPN will do is you will advertise through the switch, through the spine, or through this collapsed core, because I'll do it here actually, through this core here, that this device here with this MAC address is connected to this switch. And therefore this switch here knows if this user wants to communicate to this user, it's got to go through this way or even via this way here. And that's all what EVPN is actually doing at the end of the day, is it's doing advertising of MAC addresses and maybe optionally IP addresses. Now there's a lot more to it other than that, but really the sole function of EVPN is to advertise to this switch and to this switch and to this switch and to that switch. These are the users connected to me, so we stop that flood and learn approach. But EVPN is a lot more than just advertising. So what you have within this layer 3 network is you've got what's referred to as the underlay itself. Now EVPN would be the overlay. It goes over the underlay. And that underlay is built on IGP protocols such as OSPF, ISIS, whatever it may be. Now this is important because what you can see is that this switch here has, to get to this switch over here, it has two available paths. It can go this way and it can go that way. So what this basically means is that we've got a multi-path function, that this switch can use two different egress interfaces to get over to this switch actually here. So we're actually using the underlay, which was using these different protocols here to get to that same destination. It's a multi-path feature. And because EVPN has already signaled over to this device here that if you want to get to this host, you can go through this switch here or this switch here, this switch knows it can do load balancing. So not only with EVPN can you use the underlay with a multipath function, but you can then load balance packets going over the underlay, the overlay itself. You can load some packets to go this way and other packets to go that way and more packets to go this way and more packets to go over here. Obviously, there's a hash algorithm to it, but at the end of the day, EVPN allows load balancing. It's what's called aliasing. So basically EVPN is the advertising. It's the advertising of who's connected to what. Because don't forget, these guys here, these devices, they might roam. It might be a virtual machine at the end of the day that's actually migrated from this switch here over to this switch over there. And EVPN would then advertise over the network to this device over here where this new user's actually connected to, or this new virtual machine is actually connected to. And then it allows, as I said, multipath. It's using the underlay to have a multipath function, two or more routes to get to the same destination, load balancing, what's called aliasing, and all using an active approach. And VXLAN is just building the tunnels. It's building the tunnels from source to destination. It's encapsulating the original frame with that VLAN with new headers, UDP, IP, a VXLAN shim header, obviously MAC addressing, and then the information can be sent. So basically, this is actually the separation that leads on. It's a nice segue into the next part where we're going to go through the differences between VXLAN and EVPN from a control plane and data plane perspective. So before we actually go through what is the control plane, what is the data plane in terms of EVPN and VXLAN, let's take things quite high and talk about in Junos the routing engine and the packet forwarding engine. So in Junos there is a packet forwarding engine, and if you don't know what the PFE actually is, the answer is really in the title, packet forwarding engine. In the PFE, you are applying certain amount of filters as well as routing policies, and additionally there's PIC concentrators, there's something called a mid plane. There's really quite a few components that go into the packet forwarding engine. But at the end of the day, what it's really doing is trying to identify what is the egress interface to get to that destination. But where does the packet forwarding engine actually get all of this information from? Well, it gets this information from what's called the forwarding table, and I'll just draw it down here. So the forwarding table is actually populating, or is being queried by the packet forwarding engine to identify what policies do I need to put into place, How do I need to filter this traffic, if at all? And really, what is the egress interface to get to that given destination? And that destination is contained within the forwarding table. But the forwarding table actually derives its information from the routing table itself, or RT. And the RT has a lot of components to it as well, but basically there's lots of tables within Junos. For example, you've got inet.0 for IPv4 unicast traffic. You've got inet.1, which I think is for IPv4 multicast traffic. You've got inet.2. You've got inet.3. You've got MPOS.0, and you've even got, related to this topic, an EVPN table as well. So basically, depending on that type of traffic, unicast, multicast, multi-protocol label switching, EVPN, etc., that routing table is populated, it's given its entries by the routing engine itself. So everything really comes back to this routing engine, and in the routing engine you've got all those protocols running, such as OSPF, ISIS, MPLS or multi-protocol label switching, EVPN, and obviously a lot more. But just in summary there, you can see that the routing engine running all those protocols is actually feeding into the routing table all the possible routes to get to a destination, and what is the best cost to get to that destination. Obviously, each of these protocols are going to have different algorithms, etc., different ways of understanding what is the network, what's the topology, and what's the cost to get there. But once all those routes are entered into the routing table will then add into the forwarding table the best path to get there. And then the packet forwarding engine is fed from the forwarding table. This is the destination, this is the egress interface, these are the policies you need to apply, these are the filters you need to apply, etc., etc. But the point here is that there is actually a clear distinction between these two. We've got the control plane, and over here we've got the data plane itself. Now the data plane is really just interested in, how do I get there? How am I going to get to a destination? And then it's going to forward those frames, those packets, etc. over the network itself. In the case of VXLAN, it's going to use tunnels. It's a tunnel-based technology where we're able to encapsulate those Ethernet frames with IP UDP headers and then forward it through those tunnels over the overlay network. So VXLAN is a data plane technology. It is just interested in forwarding those frames through the tunnel, yes, through encapsulation, but it's just interested in forwarding those frames after encapsulation through the tunnel to get to that destination. But how does VXLAN know where to send those frames through? How does it know what tunnel to use? How does it know what virtual network identifier to use to get to a given destination? And that is where EVPN comes into it. EVPN is a control plane technology. It's a signaling protocol. It's signaling to VXLAN. It's signaling to the data plane. If you want to get to this destination, if you want to get to this server, if you want to get to this host, this /32, whatever it may be, you need to go through this tunnel. You need to go through this path. So EVPN is signaling to VXLAN, these are the destinations, this is how you get there, and then VXLAN is building the tunnels to actually get to that destination. That's why the two work very closely together. But again, they are separate protocols. So now we know the difference in terms of control plane, data plane, and where EVPN sits, i.e. the control plane, and where VXLAN actually sits. Why are these actually different protocols? And that really is answered by, well, what is the type of network that you actually reside in? So if I just draw here EVPN, EVPN is that signaling protocol. It's the control plane protocol. It's advertising to the data plane. If you want to get to a destination, this is where you actually need to go. This is the route you need to take. So with EVPN, you could have, as we've gone through, VXLAN. So this is very common, or becoming very common, I should say, in the enterprise network as well as in data center environments. But what about if you're actually in the service provider network? Are they deploying VXLANs? Well, they might do, to be honest. I actually don't know. But what is very common in service provider networks is they have a data plane technology called MPLS, or multi-protocol label switching. But they could still use EVPN as that control plane technology, but then in the service provider environment, they're then using multi-protocol label switching to build those tunnels from source to destination with the signaling controlled by EVPN. But you don't also need to have EVPN as the control plane to feed VXLAN. VXLAN could be fed by another control plane protocol, something like LISP or Location Independent Separation Protocol. It's been quite a few years, to be honest, since I've touched that protocol or even read about it. I think that's what it stands for. But my point here is that they are clearly two separate protocols. VXLAN sits at the data plane, EVPN sits at the control plane. They are very commonly used together, but they don't always have to be. EVPN is very powerful at the end of the day because it's based on BGP, whereas VXLAN at the data plane layer, it's a lot more straightforward. It's just building tunnels and it's forwarding frames over those tunnels based on the information it gets from the control plane itself. But depending on what type of network you are residing in, data center, enterprise, campus, or maybe the service provider, it really dictates what you're going to be using for that control plane and that data plane technology. Okay, so we're going to carry on now with the key terms for both EVPN and VXLAN. But first, let's start off with the more straightforward protocol, and that is by far VXLAN, especially when you compare it to EVPN. So VXLAN, Virtual Extensible Local Area Network. Now, I've already said really the only two key terms that I'm aware of and that you need to be aware of, and one of those are VTEP, and what this stands for is VXLAN Tunnel Endpoint. So VTEP, VXLAN Tunnel Endpoint. Some people think it stands for Virtual Tunnel Endpoint. Kind of the same thing, really. It's debatable, I know, but it actually does stand for VXLAN Tunnel Endpoint. Now, I've already gone through what this basically is. So on a switch, so let's say this switch here, you're going to have a number of VTEPs. So you have VTEP 1, VTEP 2, VTEP 3, so on and so forth. There's no, well, there will be a limitation depending on software and what the device can actually support. But you could have X amount of VTEPs on a given device. And what this is doing, as we know, it's doing encapsulation and decapsulation of those original Ethernet frames. So as a Ethernet frame comes in from a host here, say I'm connected to this switch, it's going to go, depending on the signaling, into a given VTEP. Let's call it VTEP 1, just to keep things straightforward. And it's then going to encapsulate my original frame with that overhead, that additional overhead. Now, in the VXLAN world, that is the IP, UDP header, but also we can't forget about the VXLAN header, as well as the outer IP addressing and the outer MAC addressing as well. And then it goes through the network to the destination. Let's say the destination is over here, where then this switch here will do the decapsulation of that header of those packets. So it will take off the UDP header, it will take off the IP header, it will take off the outer outer IP address, the outer MAC addressing, and then it's able to send out that original Ethernet frame. VTEP, it is a tunnel endpoint. It's also a tunnel start point, and that's a key term there. Well, moving on to another key term, tunnels, we need some kind of identifier. That is where VNI, or Virtual Network Identifier, comes into it. What the VNI is actually doing is you're taking that original VLAN identifier, and that only has a maximum of 4096, theoretical maximum I should say. Whereas VXLAN, through the VNI, where it supports 24 bits, you've got less than 17 million possible identifiers, which is significant to say the least. So what's recommended is you take that VLAN ID, say it's VLAN 500, and then you map it to a VNI, a VXLAN Virtual Network Identifier. But you do so from 5000 onwards, because VLANs only support up to 4096. So let's say we take the VNI of 5500. Saying 5000 because it's higher than the 4096 that the VLAN identifier actually supports, and the additional 500 to map here to the original VLAN identifier. So what the VNI is doing then is it's saying, well, this traffic coming into this switch that wants to get to this destination over here, I am going to build that tunnel which goes over the overlay, and check out my artistic skills here. And this is going to go through this VTEP here, and it's going to go over to this VTEP here, and this tunnel is going to have this virtual network identifier of 5500. Therefore, all traffic that belongs to VLAN in the layer 2 switching domain, VLAN 500, get mapped to the VNI, the VXLAN virtual network identifier 5500, and then they know to go over this traffic back and forth through that tunnel itself. Now, if you're wondering what the VTEP actually uses in terms of IP addressing, it is actually a loopback0.x interface, and the same over here. So you've got loopback0.x interface. I'm saying .x because in the Junos world, there's only one loopback, and that's loopback 0, but then you could have X amount of sub interfaces, or in Junos we call them units, associated to that. So you could have, for example, loopback 0.500, which corresponds to VLAN 500, which is then mapped to the VNI 5500. Those are the two key terms that you need to be aware of when it comes to VXLAN. EVPN has its own key terms as well. Okay, so let's move on to EVPN. The first one that I want to touch on is EVI, which stands for EVPN. My writing is terrible today. Virtual instance. Hopefully you can read that okay. My writing isn't as bad as what it looks like on paper. It's just using an Apple pen. Anyway, so what is an EVI? Well, an EVI is quite literally all those interfaces and devices that are participating, that are advertising, that are partaking within that EVPN instance. So we've got this device here, we've got this device here, we've got this device here, as well as these two devices up here, can't forget about them. And they are all advertising, receiving and forwarding all the prefixes that are advertised by EVPN. So quite literally everything here would be that EVI, that EVPN virtual instance. So it's quite literally the entire domain itself. That is very straightforward. That is what the EVI is. So if you ever hear that term EVI, just know you are referring to that whole EVPN instance itself. But you've also then got this other term called ESI lag. Now, I'm not going to write out the entire acronym because that would be very long, but that stands for Ethernet Segment Identifier, and then lag at the end, the link aggregation group. So what you can actually do in EVPN is you can bundle together interfaces upstream and downstream, and then advertise that, or EVPN will then advertise that bundle to remote devices, so they know that they've actually got two possible ways to get to a given destination, but the interface will appear as a bundle. So within the ESI world, what we have, just for example, is we've got these two interfaces here. We've got this interface here, and we've got this interface here. Yeah, they go into two different switches, as you can see. But from this switch perspective, really, if we bundle them together, it's then just going to see one bundle to get to the destination over here, whether it be a user or a server that's actually connected to this switch. You can see, if I bundle these together and then advertise that into EVPN, and then those advertisements come down, as I said, the switch here is going to see, I've got one bundle, I've got one link aggregation group at the remote end to get to this. So if this link goes down, I can still get to that destination via this link here. So that's actually known as the Ethernet segment, obviously lag. But the identifier there is then identifying that ESI lag itself, or ES lag I actually should say. So if you have an ESI, an Ethernet segment identifier. The identifier is giving an ID to that Ethernet segment, to that bundle. Now that is a 10 hex value, and if you are building an Ethernet segment, I've really wrote that bad there, so let me just change that. There we go, looks a bit better. But a 10 hex value would look something like this. It would appear 01.11.22.33.44, etc, etc, until you've got 10 hex values. I've only got 6 or 7 there, I don't know, I'm not counting. But it's a 10 hex value if you are identifying an Ethernet segment. If you are not identifying an Ethernet segment, it would be all zeros. So if this was not a bundle, this device here would see, actually I can see that there's 2 interfaces at the remote end to get to that host, to that server itself. Ethernet segment identifier. Ethernet segment is basically a lag which is advertised through EVPN, bundling together interfaces to advertise to remote ends, and then you're sticking an identifier within that Ethernet segment so that the remote end can see, to get to that destination there is a bundle and it's got this identifier. So ESI, lag and EVI, but then you also need to be aware of this concept of RD, which stands for route distinguisher. Now, route distinguisher is quite literally distinguishing different routes to each other. It's giving them a sense of uniqueness, and that's important because if we look at this switch here and this switch here, they could be advertising into the network, just for example, a 192.168.10.0/24 network over here, but on this switch over here, it could also be advertising in a 192.168. I'm running out of space, 10.0, also a /24. Now that's going to create some problems in the routing world, isn't it? So what the RD is doing is it's allowing us to apply a unique identifier to this route here and to this route over here. Obviously each switch would add in its own type of route distinguisher. They have to be separate, but it's allowing you to advertise and for receiving devices to receive really the same advertisements but identified differently via route distinguisher, so that receiver knows how to distinguish really the same advertisements two from one another. And there are 2 types of route distinguishers. You've got a type 0 and a type 1. Now, you don't really see the type 0s anymore, you mostly see the type 1s, but just so you know what the type 0 was it would look something like this. You would have the autonomous system number, because EVPN is BGP at the end of the day, so we're using autonomous system numbers, and then you just have a random number that is assigned by the administrator or maybe just randomly selected. So if this device here, if this switch here was in ASN, let's just give it a quick name. So let's just give it 65100, and this switch over here was 65200. You could then advertise in, say it was advertising in VLAN 500 here, and this was advertising in VLAN 500 as well. This could have the route distinguisher of 65100:500, and over here the route distinguisher would be 65200:500. So again, you can see that you're able to advertise in the same VLANs or maybe the same network prefixes, but with the route distinguisher it's able to give a sense of uniqueness to those advertisements as they are forwarded throughout the network and obviously received at a receiver end. But the problem here is that notice I've done exactly the same VLAN, so it's VLAN 500 here and VLAN 500 over here. So you could argue that actually it's not a sense of uniqueness, even though the ASN might be different. If the ASNs are actually the same, then again it's not a sense of uniqueness, and that's where the type 1s then come into it. And what the type 1 basically advertises in is it advertises in that router's ID, so the router ID, the VLAN number, or some other attribute here. Now every router, this is why it's more preferred, every router or multi-layer switch is going to have its own router ID. So this could be 1.1.1.1 just for example, and over here you could have 3.3.3.3, And thus the route distinguisher over here would then look like something like this. It would look like 3.3.3.3 colon 500. And over here you'd then have the route distinguisher of 1.1.1.1 colon 500. So if this switch up here was receiving those advertisements from these two routers, it could see, over here it's come from router 1, just for example, using the 1.1.1.1, but over here it's coming from router R3, from the router ID of 3.3.3.3. Yes, they're both advertising in the same VLAN, so VLAN 500 here and VLAN 500 here, but because of that router ID, I can uniquely identify where those routes have actually originated from in the first place. So route distinguisher, very easy, but very important when it comes to both BGP and EVPN. And the final one I want to talk about is the RT, and what this is or what it stands for is route target. Now, in my previous example of route distinguishers, those route distinguishers are being advertised up to this switch here, up to this router here, which is great. The device then, using the route distinguisher, can uniquely identify where those prefixes have originated from and a VLAN or other type of identifier that goes with that RD. But then how does this device actually know what to do with that information? And that's where the route target actually comes into it. So the route target will look like something like this. So you'd have the autonomous system number, and then you'd have some kind of arbitrary number, whatever it may be, 500 associated to the VLAN, or maybe something that's specific to that network. It's completely arbitrary, but you certainly have the ASN first and then an arbitrary value at the end of it. So what you'd have is you'd have a route target coming with the route distinguisher coming all the way up here, but then this device here needs to have that same route target, needs to have the same route target as an import policy. So you'd need to have an import policy on this device as well as an export policy on these devices as well. So export here and an export policy on this device here, and they have to match. You have to have the same route target on the devices which are advertising those prefixes, and you have to have the same route target on the device that's receiving those prefixes. So why do you need the same route target on the device that is advertising into the network the prefixes, and why do you need the same route target on the device that is receiving that route target? The reason why is, as I said, EVPN is based on BGP, or Border Gateway Protocol. That's essentially what EVPN is. To be specific, it's really more IBGP. It's not really eBGP, it's more IBGP related. But within BGP, there is this concept of communities. And communities allow an advertising router to advertise in a certain amount of prefix or a prefix, and to assign a community tag with that prefix. With route targets, what we're actually referring to is extended communities. And the extended communities have these default functions associated to them. I want to accept this, I want to reject it, or I want to maybe advertise it to only peers within my confederation, speaking about BGP, and not advertise that to peers outside of my confederation. These are extended communities. They have default functions, and a route target is exactly that. A route target is a extended community. So if you've got a community, a prefix which has been advertised to this device up here with a specific route target, that is why on this device here you need the same route target, because it needs to import that into its routing table, and it needs to know when I import this, or if I import this, this is what I want to take, this is the action I want to take with these prefixes. And when we're talking about prefixes, we're actually referring to what is known as the Network Layer Reachability Information, or NLRI. And within the NLRIs, you've got the prefixes themselves, and as I said at the beginning, even the path attributes such as the AS path, the local preference, multi-exit discriminator, origin, and a lot more. EVPN is advertising this network layer reachability information, it is advertising these prefixes, it's advertising those path attributes to and from these different sources to the destinations, to and from and throughout the entire Ethernet virtual instance, or EVI. And the route targets allow those receiving devices to know if I'm importing this prefix, this NORI, this is what I'm going to do with it. And so there we go, everybody. That is the end of this video. That is the end of part 1 into EVPN VXLAN routing, the protocols. Obviously, this has been quite a long video, and that does actually say how in depth these protocols actually are, especially EVPN. And this is only an introduction. This is only the basics of what EVPN is, what VXLAN is, why do they work together, what benefits do they bring, what are the key terms when it comes to these, and really how do they work in terms of building a tunnel, how does a switch or router know who to build that tunnel to, how does EVPN actually advertise that, etc. And that's actually a good point. We've not even gone into the details yet as to the different EVPN packet types, how it does the advertising, how you build the underlay, what you need to advertise into that underlay to allow EVPN, that overlay, to have that reachability, and so much more. And those kind of questions, those kind of topics are going to be discussed and shown in detail in later parts of this EVPN VXLAN series. So I hope you enjoyed this video. I hope you found it informative. If you liked this content, please subscribe to the channel. Please give it a like. It's the best way to support my channel. Any questions or comments, let me know down in the comments box or message me. I really do enjoy the feedback I get from you. Other than that, thanks for watching and goodbye.